Finish the notes from yesterday, so get them out. I'm going to try to run through this as quickly as I can. All right, how many did we get through yesterday? First of all, how many are there? 7 total, and then we got through number 4?
Yes.
All right, we got through specific heat?
Yes.
Is that right? Okay. All right, so now there's this thing called simple machines. Number 5 is simple. We didn't finish the other one? Well, let's go back and do that. Let's do 4. I'd rather do that anyway. Specific heat. All right, number 4. Specific heat is this idea of I have a bucket of water. I have a fire. Let's say that the fire, we measure energy in what unit? Joules. So this fire then has an energy of 1,000 joules. Are you with me?
Yeah.
All right. Let's say that there is 1,000 grams of water in this bowl or whatever this thing is. All right. And it is sitting at 20 degrees Celsius. Have you got that picture in your head?
Yep.
A fire underneath it, 1,000 grams of water, 20 degrees Celsius. Yes, we did. I'm going back through it real quick. All right. What do I want? Then we went through it yesterday. What are we going to do with this 20 degrees?
You want to raise 20 gram of it up 1 degree.
We want to raise, let's look at it like this first. We want to raise this entire thing up 1 degree. All right? Are y'all with me? We put a fire under it, so we're trying to raise temperature. But there's this thing called specific heat for every element, for every compound. There's a specific heat. And I don't know what the specific heat is for water. We're going to make a number up. But I think it's 2 joules per gram per degree Celsius. I think you're right, degrees Celsius like this. I don't know. Whatever. Per degree Celsius. So what that means is for every gram of water, and let's just make a little gram right here. For every gram of water, that little blue dot in there, all right, it takes 2 joules of energy to raise that little bitty spot of water 1 degree. Are you with me?
Yeah.
Now, how many little spots of water are in there? There's 1,000. So if it takes 2 joules of energy to raise one of them 1 degree, how many joules of energy is it going to take to raise 1,000 of them?
2,000.
Do you understand it's going to take 2,000 joules, right?
Yeah.
All right, so if it takes 2,000 joules to raise this entire thing 1 degree, is my fire big enough? No, because my fire only has how much energy? 1,000 joules. And I need 2,000 joules to raise this thing up 1 degree, so my fire's not big enough. So I got to put another log on the fire. That's funny. All right, that's specific heat. And we're going to do some math problems with specific heat later. Are you with me? That's number what?
4.
Number 4. All right, the next one is number 5. And number 5 is simple machines. All right, question. What do machines do for us? They make, okay, that's good stuff. They help us do work, make things easier, and a thing called mechanical advantage. All right, now you should be knocking these notes out. Look, where did you get mechanical advantage from? How did you know that? The board. Good. Now that's fair enough. Because when you come in, this mechanical advantage is one of the, there was 3 things that are difficult in this. Phase diagram, specific heat, and mechanical advantage. All right, we're going to talk about mechanical advantage in a minute. But let's look at simple machines. All simple machines do is they help us do work. All right? Now, here's the deal. That's really all they do. I'm going to give you kind of a list of simple machines. Here's something called a lever. All right? So we have a box on this end and a dude over here pulling the box down. When he pulls the box down, if this side that he's on is longer than the side that the box is on, it makes it easier for him to do work. Are you with me? We're going to talk about how that is. if you have a pulley, there's a guy down here pulling on trying to pick a box up. Instead of him lifting the box up, he can pull down on the box, and therefore he can help, and gravity can help him pull down to help raise the box up. Are you with me? Simple machine. Okay, are you getting there? Ma'am?
What is that a picture of at the bottom?
This is a pulley. And this right here is a lever. And there's a bunch of different simple machines. All right, but what simple machines do specifically, well, we're going to get through this pretty quick. What simple machines do is they help us do work. Now, if they help us do work, there's a formula for work, and work equals force times distance. All right, work, force, distance. Is that a simple formula or a complicated formula? That's a simple formula. Okay? Work equals force times distance. So, I want to show you what the definition of work is. To get to the definition of work, what is the definition of a force? A what? I heard it. A push or a pull. All right, now watch this. Am I doing a push or a pull right now?
Yes.
What am I doing?
Pushing.
Pushing on a wall. So there is a force that I'm pushing against the wall with. Amen?
Amen.
All right. So, am I doing any work?
Yep.
Is the wall moving?
No.
The wall moves. Let's say that I'm pushing with a force. Let's clean some of this up right here so I can put some numbers in. Let's say that my force is 10 newtons. And the wall is not moving, right? It's no meters. Am I doing any work?
No.
No, because 0 times 10 is 0. So I can try to pick this thing right here up all I want. And I'm straining and struggling, but I'm not doing any work because the table's not moving. Are you with me?
Yep.
All right, so we have to have a distance to do any work. Now, looking at these two simple machines here, and like I said, there's about 5 or 6 of them, but we're going to look at 2 right now. Let's go to another flip chart and let's make a lever because they're pretty easy to see. Now watch this. This is real simple stuff. If this right here, if for me to lift this box straight up to pick it up, it may take a force of 10 newtons. Are you with me?
Yes.
It may take a force of 10 newtons for me to pick it up. And if I want to lift it, let's just say 1 meter, then my work then is 10 Newton meters. That's how much work I've done when I lift the box up. Are you with me? Now, if I'm standing on this side, now that's if I'm over here picking this box straight up by myself. But if I'm over here, which way am I going to, what do I have to do to lift the box up on that side? I have to pull down, yes? But watch what happens. For me to put, if these two, let's say that these lengths right here, let's say that this is 2 meters and this is 2 meters. From here to here and from here to here. If these are equal, I have to still pull down with 10 newtons of force. And I have to still pull down 1 meter. I have to pull this down 1 meter to lift that 1 meter. Are you with me? They're equal. Yes?
Yes.
However, if I do something like this, now, whoops, my bad. If I lengthen this thing so that it is, instead of 2 meters, how many meters is it now? How many is this side?
4.
It's 4 meters. Come on, Higgy. It's 4 meters. Now I'm over here picking it up. Or actually, I'm not picking it up. I just made it easier for me to lift this box. Because now I have an advantage. I have what is called a mechanical, write this down, mechanical advantage. This is the last part of the notes right here. I have what is called a mechanical advantage. This right here is just telling me that I have a machine, sounds like mechanical machine. I have a machine giving me an advantage. And the reason that it gives me an advantage is this. Let's draw the lever down here with this thing on the ground. This is 4 meters. This is 2 meters. The box is sitting here. Now, if this thing is 10, it takes a force of 10 newtons, and I want to lift it 1 meter, but I'm standing over here. What do you notice about the distance that I've got to pull down compared to this distance raising it up? I've got to move it more, right? I've got to reach farther up and pull it down to just get this side to go a little ways. I've got to pull this one down a long ways. Yes? And the reason for that is because I'm really now only having to pull down with 5 newtons of force, but the box weighs 10 newtons. Now think about that for just a minute. I only have to pull down with 5 newtons of force because of the longer arm, but I have to pull down. Guess how many meters I have to pull this thing down? I have to pull it down twice the distance, 2 meters. So that when I multiply these, I get 5 newtons times 2 meters is 10 newton meters. And when I multiply this 10 times this 1 over here, I get 10 newton meters. Both sides are the same amount of work. Force times distance, force times distance. This is the same amount of work, but the way I got the work done was that I pulled down twice as far, but I didn't have to use as much force, and that's what machines do. They reduce the amount of force that I have to use, but they increase the distance that I have to do it. Are you with me? One last quick example is this. Here's what is this called? It's called a ramp. All right, you with me?
Yeah.
All right, let's say that I have a box right here, and I want to lift this box 2 meters. And I'm standing over here, and I want to pick the box up 2 meters. Watch this. This is pretty interesting. I want to pick it up 2 meters, and it's also 10 newtons of force to pick it up. All right? You with me? Let's say that this thing right here is, I want to lift that 2 meters. Let's say that this length of this ramp is 6 meters long. All right? So instead of picking the box straight up, because it's heavy, all I do is I put the box on this ramp, and I push it up the ramp 6 meters. I had to push it 3 times farther than I still got it 2 meters in the air because I pushed it up the ramp. Yes? Yes. But I had to push it 6 meters. So I had to push it 3 times as far. Does that make sense? Well, guess how much force I had to use? If I had to push it 3 times as far, was it easier to push it up a ramp, or is it easier to pick it straight up? It's easier to push it up a ramp. So if I had to push it 3 times as far, then it made it 3 times as easy in terms of the force that I had to use. So what I do then is I take 10, divide it by 3, and I wind up with 3.3. That's how many newtons of force it took me. So I pushed it 6 meters, 3.3 newtons of force. And if you multiply those together, you'll see you'll get 20. And if you multiply those together, you'll see you get 20. It always equals out. So if we reduce the force with a simple machine, we increase the distance we have to do something. You with me? Yeah. Yes? All right. Now, that's good, and you're awesome. You can turn